All right, guys, so I'm taking this video just as we left the classroom, and I sent you guys an email. First, apologizing for, the mess today with the computer. Definitely was not helping. But if you guys have any questions about anything today, even if it was strange because I couldn't get to a table or I couldn't see the screen, just please ask me. Just come to my office hours, send me an email, even like try to see me outside of office hours, and I can go over it again. All right, now if you look at my notes, all right, that I posted online, there are about 8 pages on convection and radiation. Now for conduction, we had this exposure to the equation for the first time in chapter 1, which is, it's good because we're going to be working a lot with conduction for the next month or two. However, convection and radiation, we're not going to see that till the end of the semester or the second half of the semester, okay? So if you look at my notes, I'm just going to follow them for now, especially for convection, and then radiation, just an introduction, okay? So you have to watch this. I mean, hopefully you're not going to skip this. I'm not going to ask anything about this on the homework. I'm not going to ask anything about this on the exam. But we're going to see convection as a boundary condition for conduction later. So I hope you guys are watching this till the very end, okay? All right, so if you look at my notes, I'm just gonna follow it, all right? It says 1-7 convection, just in case you are following the textbook, and then it says moving right next to it. We have heat transfer due to convection. We have fluid that is moving. Someone asked me a question at the end of the class that they had their drink. Is it faster if it cools down if he just leaves it out on a table exposed to air that is not moving, or will it change the temperature faster if there is air that is moving around it because there's a fan or an AC unit or something? And this depends, right? Depends on the temperature of that fluid that is moving for convection, depends on the temperature for conduction. It depends on many factors, okay? But for convection, something is moving. For example, I have this container of Aleve, okay, and it's really cold. I'm not sure why it will be cold, but it's really cold, and I want it to warm up. Should have thought of my prop before I started recording. And if I just leave it out here, okay, it will take a long time to warm up. However, if I have a moving fluid, all right, moving fluid at a higher temperature, then this will increase the temperature faster than if it's just exposed to air that is not moving, okay? So if you look at the notes, it says mode or mechanism of energy transfer by heat between a solid and a fluid, right? And that fluid is a liquid or a gas. So again, I have my solid, and maybe, all right, I will have conduction through the solid and then convection, all right, when we have a moving fluid. We will see convection later on, and we have to review a lot of fluids before we get to talk about convection. And then there you see on the notes, velocity profile and temperature profile. If I have that hot surface, actually this was cold, so I'm using a different example. If I have a surface at a certain temperature, okay, then it makes sense that the velocity profile is that way. So velocity is 0 at the surface, and then it increases until I have that bulk velocity, okay? Temperature profile, it will be different if, the surface at a higher temperature than the fluid that's moving on top of it, then the temperature will be decreasing as you move away from that surface, right? And that makes sense. It's just decreasing all the way to the fluid temperature. And there you see that temperature profile, high temperature to low temperature. So Q will move in that direction. So here I said the example is air used to cool down a hot surface. The temperature profile, we'll see that later on for convection. And we see that Q is in that direction from the surface to the fluid, right? And that makes sense. So this energy is moving from the surface to the fluid. So that means that the surface temperature will decrease, okay? All right, for convection, instead of having an equation that turns into a differential equation, you will have the Newton's law of cooling that you see over there, H, okay, which is the convection heat transfer coefficient multiplied by the surface area, multiplied by the delta T. This is very different. We don't have here the delta X and the delta T anymore. So here, we tend to have high minus low temperature. Sometimes we see T surface minus temperature of the fluid. Sometimes we see it the other way, temperature of the fluid minus T of the surface, and we just have to be careful with our diagram in what direction it's moving, okay? So it looks easier, you know, it doesn't look like we're going to turn that into a differential equation. The issue is with that convection heat transfer coefficient. Again, I'm following my notes. It's very hard to find, okay? It depends on so many factors. It depends on the geometry that you have. It depends on the type of fluid that's flowing. It depends on the velocity of it. It depends on whether it's laminar or turbulent, and that's why we need to know fluids, okay? So that convection heat transfer coefficient, it is not trivial to find, okay? So it's not like a table we find the conductivity, nothing like that, right? So now I moved on to the next page. Depends on so many factors that we'll get to that later, and hopefully it'll be better as I show it to you and not a mess like today with the computer. All right, so then it says there, why so much detail for conduction and not for convection? So because conduction is going to be like half of the semester, okay? Now what about enthalpy? Because there's that H. Isn't that enthalpy? You guys remember enthalpy from thermal? It was U plus PV. Well, it's also H, right? Other textbooks, they change enthalpy all of a sudden to I. Things get confusing. So we are going to be very careful if there are any equations that have those two values, but typically we don't have that in this class. And then conduction and convection, and they happen at the same time, yes. And then you see a little diagram over there, okay, where we have, you know, again, we have, I don't know, this is really, really hot, okay? And then there's air flowing through here. I have a fan because I need my calculator to cool down, all right? I'm going to have conduction inside, all right? Conduction inside. And I'm going to have convection inside, all right? So I'm going to have Q conduction all the way to the boundary and then convection after that. And if we make, if we analyze this the surface, then the two of them are equal, all right? But we'll get to that later. That's it for convection. Isn't that great? All right. That's not going to be on an exam, and that's not going to be on homework. However, as I mentioned, for conduction, in many cases, we'll have conduction for, you know, whatever we are analyzing, and we will need boundary conditions to solve our differential equations. And in many cases, the boundary conditions will have to do with convection. So the problem will tell us the convection heat transfer. Wait, the coefficient. Yes, convection heat transfer coefficient. I apologize. Today I am, all right, it's not just today, the whole week. Right, so the coefficient, the problem will tell us that the value, and then we can just move on and analyze the problem using convection at the boundary. Now the next topic that you see in your notes, radiation, all right. Initially, I wrote a lot for radiation, and then I realized that radiation is at the very end, and I will go over radiation 3 days at the end. Even if I have not finished heat exchangers or internal flow, whatever else you have to do, I will do 2 or 3 days of radiation. So we're not going to go over all of these notes. I'm just going to go over some of it now. I want you guys to remember that this is always present, always. You can look at the definition there. It says energy emitted by matter in the form of electromagnetic waves. So we're going to be studying thermal radiation. So we're not going to be talking about X-rays or electromagnetic radiation. So this does not require the presence of a medium. Like here, if I want conduction, I need this material, right? From here, from the center, let's say, to, you know, this is a cylinder, to the surface. But for radiation, I don't need it. Actually, radiation works best when there is a vacuum, all right? So similar to convection, we will just introduce this for now. But again, there are a lot of notes that I wrote over there that I will not go over now, okay? The equation for Q dot for radiation, there is a derivation on the notes that I'm not gonna go over, but it is a function of T to the 4th power, okay? And we will see all of this later. I want you to see that. It's T to the 4th power and not just T like we have for conduction and convection, okay? So again, this, all of our systems emit radiation. Like Aleve, yeah, Aleve is great. So this is emitting radiation right now, and so am I, and so are you, okay? But doesn't mean that this value is significant, okay? So again, for radiation, what I want you to know is that it's always happening. It does not require a medium in order for it to go. Like for convection, we need the fluid, or for conduction, we need our solid. It doesn't require that. And it's always there, and it's a function of t to the 4th power. Now, all of those pages after that, okay, I'm going to cover that later, like the textbook does later. So after this, we're going to skip to the very last page where it says review. For the review, this introduction I might change future semesters now that I realize that there's a lot of information that I need to add and that I need to eliminate. Q is different for depending on what's happening. We have kilojoules, kilowatts, or we have kilowatts per meter squared for heat flux, and then you see some units on the other side, and that last one over there has to do with radiation, so we don't have to worry about that one right now. And then I want you guys to have some familiarity, can't say that word, with conservation of energy for closed systems and open systems. If you are struggling so much to understand those equations, please come see me, all right? One side is crossing the boundary, one side is changing side, and like for example, the equation that we saw today for conduction, then we will substitute that Q into that Q minus W delta U. And that's how we get the equation, the governing equation that you have seen on the PowerPoint, okay? There are also some approximations that you see over there, delta U and delta H, and that is for an ideal gas, the first one that I have over there. The delta U and delta H is a function of CV, CP, and delta T. And then for an incompressible substance, I would say that density does not vary with changes in pressure. Then we say that CV, CP, and C are very close and the values are very similar. So you are welcome to look that up on a table if you want. And then after that, what's important is the different modes of heat transfer. You need to be able to solve that equation for, delta T, delta X, because we're already assuming so much there, but then the textbook doesn't tell you what we're assuming until we get to later chapters, okay? So for conduction, it's not moving. We have negative conductivity times area and dt dx. The negative because if I'm moving from high temperature to low temperature, okay, high to low, then here, this will be 2 and this will be 1. All right, I'm going to have T2 minus T1, X2 minus X1, and that will be negative. All right, someone asked me, can I just use the absolute value, delta T, delta X, and not have the negative? Sometimes we don't know the direction, and that's one of the things that we're trying to figure out, so we need to be really careful with this, okay? For convection, it's moving, and the heat transfer coefficient, the convection heat transfer coefficient is not trivial how to find that. We need to know a lot of fluids, and radiation is always present in that equation down there. Don't worry about that. It's a function of T to the 4th power. So this is all I want you to know, what's on this page. You don't need to know how to solve any problems yet. Maybe at least understand a little bit why we have that negative for conduction, okay? So thank you for being really patient with me so far, and I hope you have a nice rest of your week.